Okay, this lesson is on density curves. So a density curve is a graphical way for us to find probability. It is used for continuous data rather than discrete data. So when we've been finding probability so far, we've been using probability rules for discrete data, which means countable outcomes. So for instance, if we roll the die and we want to know how many times do we roll a 6, there's no decimal values in that. We either roll a 6 once or twice or 3 times, or let's say, for instance, flipping a coin, right? And counting maybe the number of heads. You can't have 1.5 heads. You either have 1 head or you have 2 heads. So again, that's discrete data. So we have probability rules to find those. But for continuous data, we could have values that are decimals. So for instance, if I wanted to find the probability that a fish weighs more than 3.5 pounds, okay, so I would need a different way to find that probability because we don't just have 3 or 4, we have 3.5 pounds. So we use a graph in order to show those probabilities. That graph is called a density curve when the total area under the curve is equal to 1. And the area of any region corresponds to the probability of that event happening. So those are just some rules about density curves. Okay, so we're going to take a look at our first density curve. And this density curve is a constant distribution. So we notice that the x values range from 1 to 5. You can barely see that 5 on the screen. But more importantly, we can get values in between these. So we could have 1.5, for instance, or we could have 2.5 or 2.2, right? So we could get any numerical value between 1 and 5. And we can find the probability of getting any area, really, because of this graph equaling 1. The area of the shaded region that I want to try to find is corresponding to the area of the rectangle that we see. So if you remember, area is found by multiplying length times width. So notice here that the length of this rectangle is 1, 2, 3, 4 units, ranging from 1 to 5. So the length is 4. And the width is 0.25, it looks like. So the distance from here, 0, up to here is about 2.5, 0.25 rather. So if we multiply those two numbers, 4 times 0.25, we do get the total area is 1. So this is a density curve, so we could find the probability of any particular region that we want by seeing what portion of the rectangle would be shaded. So for instance, if we wanted to find the probability that x is less than 3, if I look here, 3 is there. And if we want the probability less than that, I would shade everything to the left of that line. That area of that smaller rectangle that I'm shading is going to be corresponding to the probability that we have something in that region. So if I look, I need to find the area of this smaller rectangle. I'm going to multiply the length, which is 2 units, by the width, which is again 0.25 units. So if I multiply 2 times 0.25, that's going to give me the probability, which corresponds to the area of this region. So 0.5, which makes sense because 3 is exactly in the middle. So that means 50% on the left, 50% on the right. Okay, the next, number 2, I'm going to actually erase number 1, so there's a little bit more room there. Number 2, we're looking for the probability that the x is between 4 and 5. So 4 is here, 5 is the edge of that distribution, so I'm finding again that rectangle. The length is just 1 unit, and the width is again 0.25. So if we find the area, I would multiply length times width, and that's going to correspond to the probability of 0.25. Okay, this next example, we're looking for the probability that x equals 2, but on a density curve, we cannot find the probability of a single value because there is no area. Technically, this is just a line, and a line does not have a thickness. It does not have an area. So we would say that this probability is 0. And then the last example, the probability that x is less than or equal to 2. This is actually the same as the probability that x is just less than 2 because, again, a line has no thickness. So there's no difference between less than and less than or equal to. So we're just going to shade to the left here. And again, that's a small little rectangle, length 1, width 0.25. And so if we multiply those, 1 times 0.25 is again 0.25 for the probability. So with a density curve, if you find the area of the shaded region, that corresponds to the probability that the event will occur. We can't have probability of a single data value with no width or thickness. Those are each 0. And there is no difference between less than and less than or equal to, or for that matter, greater than or equal to or greater than. These two are viewed as the same area, the same probability as is less than and less than or equal to. Okay, here's an example of a density curve that is not a constant distribution. If we notice, it's left skewed, so it has smaller probability on the left side and larger probability on the right. It's kind of triangular shaped. Okay, we would find the probability the same way, find the area of the shaded region. So if we look, the first one, we're looking for the probability that x is less than 0.25. So if I go to where x equals 0.25, and shade less than that or to the left, we see that that's a triangle. So area formula for a triangle is 1/2 base times height. So the base or the bottom of my triangle is distance 0.25. The height of my triangle is also 0.25. So if I plug that in, 1/2 0.25 times 0.25 is going to give me that probability, and again, which corresponds to the area of that triangle. If I multiply those, I get 0.03125. And this is a probability, so again, I could write it in any form. So that's the decimal. I could change it to a percentage if I want, 3.125%. And we see that that is a pretty small area, so it makes sense that the probability is small. Okay, number 2, I'm gonna erase that. Number 2 says we want to find the probability that x is greater than 0.75. So 0.75 is over here, and greater than I would shade above. Now, that's kind of tricky because the shape that we see is a trapezoid. You might not remember how to find the area of a trapezoid, so we're going to actually find the area of the complement. Oops. And then use the complement rule. So if I find the area that I don't want, notice in blue, that is a triangle. And hopefully we just did an example with area of a triangle. So hopefully we know that formula, 1/2 base times height. So again, because these are probabilities, you can use complement rule whenever you want. So if it's easier to find the opposite of what you want and then subtract from 1, again, that might be the easier route to go than to try to remember the trapezoid formula for how we find area. Okay, so the area in blue, we would take 1/2 the base, which is 0.75, times the height, which is also 0.75. So 1/2 0.75 times 0.75. That's going to give me this area in blue. Let's find that value. Okay, the area in blue is 0.28125. Again, that is the opposite of what I want. That's the complement. So I'm going to take 1 minus that probability, and that's going to leave me the probability in pink, which that's the probability that I want. So if I take 1 minus 0.28125, I will get the probability in pink, which is 0.71875. Okay, so again, some of the situations, it might be easier for you to find the opposite and then use complement rule. Okay, this concludes our notes on density curves. Other than, I just want to say that one of the most popular density curves is the normal curve. So we'll be doing some more work with the normal curve and finding areas under the normal curve in future lessons, which will correspond to the probability for those density curves as well.